Hey guys, last time we dealt specifically with the concept of continuity. We only really had time to go through the definition of continuity and talk about it in relationship to a graph. Today we're going to continue that trend by looking at some more graphs using Desmos. And then afterwards we're going to look more at how to understand a function in terms of continuity without needing a graph. We also discussed one-sided limits last time, where you take a limit and you approach it from either the left-hand side or the right-hand side to determine how the function is acting in each of those two domains, because it can be different depending on the function. Your left-hand side, as you approach a value, may act very differently than your right-hand side, or vice versa. It's important to note that each one of those has specific definitions and meanings. Again, we can either do that numerically by looking at numbers that approach it from either the left or the right, or we could look at it in terms of from a graph. The analytical approach is less useful. That doesn't mean it's not useful at all. So we're going to look at those kinds of problems too, determine kind of how they fit together, and from there see how these graphs actually talk about it. So let's review first of all by talking about continuity. When it comes to continuity, the important part is the three-part definition. Part one. Let me pull my notes. There we go. Part one. The value has to exist, meaning actually has a number value. It can't be going to infinity or negative infinity. It doesn't work. It has to actually be a definable value. In other words, it can't be an open circle in the middle of the graph. Two, the limit has to exist. That's a big detail. Because remember, to define a limit existing, we talked about how the left and right-hand sides have to agree that this is the value. So the left-hand side and the right-hand side have to agree upon what the value is, and there has to be a value there. Part three is the connective glue. Not only does the left-hand side and the right-hand side have to agree, not only does the value have to exist, but the value has to exist where they agree. So there can't be any jumps or holes, as they're sometimes called. I like to imagine continuity as a roller coaster. Take a look. So, if I take my picture, and then I get a little graph. And I make this graph a little wonky, so to showcase kind of different kinds of discontinuity. Okay. Imagine a little roller coaster, a little mine cart, maybe Indiana Jones style, on your graph. Okay, this roller coaster can travel up and down your graph as it sees fits, and of course, as it's coming up, you get the as it's pulled up along the graph. But here's the thing: this is a hole. Now, if this is an actual roller coaster, your little roller coaster is going to plunge through this hole, and you're going to, die. You die here. If this is a real roller coaster, holes in your roller coaster, it means death, or at least very serious injury, okay? So in this case, this is a place where we have discontinuity. Discontinuity means death. So if I'm on my roller coaster, hey, I'm on the roller coaster, I'm on the track, I can keep going, I'm doing good. I get to here, there's a hole. And what I mean by hole is, even if there's a dot up here somewhere that fills in that hole, supposedly, right, fills it in, I still, when I get there, I fall through the crack, and I die. So this is an example of discontinuity. If I was to continue along my track, let's say I pick up right where I left off with a brand new set of passengers, and then I get down here, this big place, this is often referred to as a jump. And it is also discontinuity. Because again, if I'm on my roller coaster, going down my track, I get to this point, my roller coaster, falls off the track, and I die. Because again, there's no ground down here. It's an infinite fall. You're dying. Okay? I don't know how you're dying, but you're dying down there. And so these are referred to as discontinuities. These are places where the function stops working. Now, there are two main types of discontinuity. Continuity refers to the ability of a function to be predictable, right? It means that there's a value and the limit approaches it, right? This three-part definition. Discontinuity refers to times when that isn't true. Because if you look at this graph, up until this point, we'd say this little red graph is continuous. Because at every point, if I asked about this value, we could find the limit at that value, and we could find the actual value there, and they match. If I ask about this value, right, we could determine the limit there, we could determine the actual value there, and they would match. It's only in places like here and here where this function is discontinuous. So discontinuity tends to happen at a point. In fact, there's only a select few functions that are discontinuous everywhere, and those are functions that you will never deal with in high school. So discontinuity tends to happen at a specific point, which means that we're dealing with x values. Because there are places where the function is going to break down. Now, there are two different types. There's what's called removable and non-removable. Removable discontinuity refers to holes in the graph. So this is an example of removable discontinuity, because it's a hole in the graph, right? The limit exists, but the value doesn't. That's the big way to think about it. Non-removable refers to jumps or asymptotes. I didn't show an asymptote on this function, but let's look at another graph, which will showcase all three. Okay, so in this example, you can see there are three different discontinuity places, right? There's going to be discontinuity here because there's a jump, which means that this x value, whatever that value is, would be a place where there is non-removable discontinuity. Here would also be discontinuity because there's an asymptote. In this case, it's going towards negative infinity down here. Now, this is also non-removable because in many ways, I couldn't plug this hole. It's an infinite hole. There's no way to plug it up. Whereas this one over here, this x value, notice I'm ignoring giving specific numbers because I just made up the graph. So in these three places, they're all discontinuity, but they're different kinds. So this one is non-removable. This one is non-removable. This one is removable. So you have holes, you have jumps, you have asymptotes, and they all describe discontinuity. But again, something that I have to stress specifically. Up until this point, this function is continuous, right? Every value exists, every limit exists, and they agree, right? There's no weird things happening on this function. In fact, for many functions that you have dealt with in the past are continuous functions. Let's start making a list. Common continuous functions. These are functions that are continuous everywhere. Lines. Every line is a continuous function. 2. Quadratics. Or, parabolas. Really, any polynomial should be continuous. Okay? 4. Radicals tend to be continuous, at least in their domain. There's radicals kind of places where the domain fails. This is a little misleading. But radicals in general tend to be continuous functions. And some of your basic trig functions, like sine and cosine. Ones that are often discontinuous at one or more points. Again, these are relatively common functions. Let's see. I guess I could also put on this list absolute values. Okay, some common ones that contain discontinuity. Let's see. Rationals. So ones that have fractions involved. These can often have points of discontinuity. Tangent functions. have oftentimes points of discontinuity. Same with some of the other ones like cosecant, secant, and cotangent. They all have discontinuities. So discontinuity in trig is really common, but in algebra, continuity is really common. Let's see, other ones that often contain these. Rationals is such a big category, like I'll put a lot of exclamation points here. Rationals are a big problem, and if you don't see how they fit together, it can be really big. So let's look at some examples of functions that might or might not be continuous. And then, of course, the other big one that can be is piecewise. Now, piecewise can be continuous, but it's just more common not to be. Rational can be continuous. It's just more common not to be. Let's take a look at some examples of functions that contain continuity in some of their domain, but not all of them. Let's take a look here. There we go. I'll spread this out a little bit. We can see a little better. Oops. There we go. And close. Better. I wish it was easy to do on my program. Okay. Whew. So, my first function I'm going to use is 1 over x. So I use the function 1 divided by x. So if you look at this function, you can see to the left here, every value exists. You can see that quite clearly. Up until we get to 0. And so in this example, 1 over x is a function that's continuous in a lot of different places, but there exist places where it is discontinuous. So how do we talk about that? How do we write that? Let's take a look at how to do that. If I have the function f of x is equal to 1 over x, there's two ways we can talk about it. We can talk about continuity and discontinuity separately. But it's far more common just to talk about discontinuity. Because discontinuity is so rare, it's more common to say, to assume continuous everywhere except. It's continuous everywhere except these places where it could happen. So let's look again at that other function. So we'd say that this function is continuous everywhere except x equals 0. So there's discontinuity when our x value is 0. Notice that we only refer to the x value because the y's can do all kinds of stuff, and it doesn't matter. Discontinuity has to do with the x values. And we can also describe the discontinuity. So in this case, this is discontinuity at x equals 0 that is non-removable. So these two ways of talking about discontinuity are really important because we define where it's discontinuous and how it's discontinuous. So for every function, you want to define where and how, because those two pieces are really important. And you may have multiple wheres and you may have different hows, so make sure to pair them together. Let's look at our next function. Our next function is, there we go. You see that many of these are going to be rationals. X, just a second, to the second, minus 1, divided by x minus 1. So, this is a function that looks to be continuous. In fact, if I start with my little slider here, I can see that every value exists and every value is predicted. There's just one small issue here, right there. So you can see how jumps are easy to see, asymptotes are easy to see, but holes are a lot harder. And so that's why they're referred to as removable, because they're easy to miss, right? They're removable from our picture. And so it's easy to fill in this gap mentally in our brain and on the picture. It's easy to fill this in. So let's talk about how to write that thing. For the function f of x is equal to x squared minus 1 over x minus 1. We talked about where it's discontinuity, so we'd say it's continuous everywhere except okay, in this case this was at x equals 1, and we call it removable. So again, we list where we're having problems at x equals 1 and how we're having problems with removable discontinuity. So it's continuous everywhere except x equals 1 where it has removable discontinuity. That's how we talk about this function in terms of its continuity. Next one. Okay, my next one's going to be piecewise. So let's take a look. In this case, I have the function, let's see, f of x is equal to the first thing, which is I have x greater than or equal to, I need the things so I can see it. Greater than or equal to, nope, just greater than, sorry, greater than 0, and the function is x plus 1. And I have f of x is equal to, equation x is less than or equal to 0, and we have x squared plus 1. There it is. It's a semicolon, not a comma. Okay. So, in this example, this function is actually continuous. Like if I come over here and grab my points, like every value has a value, and the limit seems to match up, including right here. So we'd say that this function, in general, is continuous. So how do we write that? We'd say f of x is equal to x plus 1 when x is greater than 0, x squared plus 1 when x is less than or equal to 0. We'd say this function is continuous. There's no places to talk about where it's not continuous. We just call this function a continuous function. And so this is an example of a continuous piecewise function. Remember, we said that piecewise is on the discontinuous list, but it's not always. It's possible. Okay? Lines are always continuous. Parabolas are always continuous. Polynomials are always continuous. But piecewise, these can either be one or the other. So it's entirely possible. In fact, I can showcase how this changes just by making one small difference. If I make f of x equal to x plus 1 and x squared plus 2. If I make just one small change, this will cause my function to be discontinuous at a specific point. Let's take a look and go to my graph. Oop. Now instead of being x plus 1, I replace it with x plus 2. Now we can see how there's discontinuity, because to the left here, I'm getting values. At 2, I get a value, but down here, I do not get values. So how do we talk about that? We'd say it's continuous everywhere except, in this case, that was at x equals 0, because that was the point on the x-axis where we had problems. And because it's a jump, we would say this is non-removable. That's how we talk about discontinuity. We'll do one more. This time we're going to go to a couple trig functions. So let's talk about sine. There we go, nice and simple. So you can clearly see that if we drag our little counter along, every function has a value. Yay! It's beautiful. So we'd say for this function that if we were to write down f of x equals sine x, we'd say this is continuous, as we listed on the previous page. But But now let's look at f of x is equal to, cosecant of x. So this is one of the list of ones that is often discontinuous. Let's take a look. So I do cosecant of x. So you can see here how there are clearly places where the function just stops working, right? I have to suddenly make a big asymptote shift. Now, where does that happen? Well, in this case, this one appears to be close to, and this is where knowing trig helps, because you might already know these values. This one appears to be centered around -3 as a jump, around 0 as a jump, around +3 as a jump. Looks like a little after 6 as a jump, but it turns out for this function, if you know your trig functions well, then you can actually make some good predictions. This is continuous everywhere except -2 pi, -pi, 0, pi, and 2 pi, and the trend continues in both directions. Or if you took trig, you might have learned to write this as pi k, where k is within the integers. Just, different ways of writing it. But the important thing is to note where their discontinuity is, and these are all non-removable. Let's look at a function that contains both. So in this case, I'm actually going to make a very simple one, very similar to one we've already used. In this case, I'm going to make x minus 1 divided by, I'm just going to reverse the order, x squared minus 1. So in this case, you can see how there's clear discontinuity over here at -1. So let's go to our list and make some space. If I'm using the function f of x is equal to x minus 1 over x squared minus 1. So we took this function and just flipped it over. So we can see how there is non-removable discontinuity when x equals -1. There's actually one more place. Go back to that function. If I come over here, like every function has a value. So it has value everywhere. And there's no like jumps or holes or anything. Good. I go over here. Every functional value, every value. Whoa, wait a minute. So over here, there's another place where this function breaks down. But it's different in this case. So in this case, we have non-removable at x equals -1. We have removable at x equals +1. Now, the trick is a few different things that are really important. How do we determine removable versus non-removable analytically? Okay, in other words, how do we find discontinuity using the equation? Well, there's a couple of little helpful rules. First thing, if you ever end up dividing by 0, there's going to be discontinuity of some kind. And this is the most common problem we're going to look at, is when we end up dividing by 0. The other option is piecewise at boundaries. If you've got a piecewise function, these boundary values are the most common places to have discontinuity, so you need to check around the boundaries. And the third thing is trig. These ones are specific and special. The fourth is when it comes to radicals, anytime the radical ends up being less than 0. There's going to be discontinuity because they're going to be imaginary numbers. Now, where it's going to be continuous is, everywhere that doesn't break one of these main rules. So how do we determine whether it's removable or non-removable? Let's look at that specific example. We had x minus 1 over x squared minus 1. Let's look at this specific example to talk about how we can tell which kind of discontinuity we're going to get. So from the graph, we knew that x equals -1 was non-removable, and x equals positive 1 was removable. And this is from the graph. How can we get that from this equation? It's actually pretty simple. How do we get it? We factor. Now, in this case, it's removable if it factors and cancels. It's non-removable if it factors and does not cancel. Because what's going to happen is when we factor this thing, we're going to find places where it could equal 0. Let's take a look. In this example, we can rewrite this function as x minus 1 on top and x minus 1 times x plus 1. In this case, I use difference of squares to factor this. But take a look. Notice that on the bottom we have these two pieces. We have x minus 1 and we have x plus 1. Now, if we take these and solve these, because remember, our goal is if we ever divide by 0, so if I take this piece and set it equal to 0, take that piece and set it equal to 0, I get x equals 1, I get x equals negative 1, which will notice that if I just do that for the denominators, I can find where the discontinuity is, right? I got negative 1, I got positive 1 over there. But the trick is it removable or non-removable? Well, if you look here, you can see that the negative 1 and the negative 1 are going to end up canceling, which is what makes this removable. Because I can literally remove it. Whereas these end up being non-removable. Because there's nothing to cancel it with. So it's removable if you can find a way to cancel it with something on top. It's non-removable if you cannot find something to cancel with. Let's look at another one real quick. Same basic function. In this case, I'm going to have, so this will test your factoring abilities today. I have x squared plus 10x plus 25 over x squared plus 11x plus 30. So here, I can rewrite this function by factoring, so I'm going to do that. I factor the top. I'm going to factor that quickly because you guys should be good students. You should know how to factor well. This becomes x plus 5 times x plus 5. On bottom, we get x plus 5 and x plus 6. Now, this will mean, because of this, I want to look for any place where I end up dividing by 0. So I take these two pieces, the x plus 5 and the x plus 6. I set them equal to 0 and find when they're going to be equal to 0. This one is x equals negative 5. This is x equals negative 6. So these are my two answers. These are two places where I will have discontinuity. So the question is, what kind will I have? Well, I can see here the x plus 5s are going to end up canceling, which is what makes this one removable. By comparison, this one has nothing to cancel with, which is what makes it non-removable. Before I graph this, take a look at this function and see how we did it. We factored the original function. We took the denominator only, right? These are pieces of the denominator. And we took those pieces and we solved them for zeros and got these two numbers, negative 5 and negative 6. And then we see if any of them canceled. The negative 5 would end up canceling, which makes it removable. The negative 6 ends up not canceling, which makes it non-removable. Well, let's verify that. I'm going to type this function into Desmos and show that these 2 points of discontinuity do in fact emerge. Let's take a look. I have on top, oops, on top, x squared plus 10x plus 25 divided by x squared plus 11x plus 30. Okay. Let me zoom this out a little bit so you can see a little better. Okay, I can clearly see over here that at negative 6 is going to be discontinuity, right? There's this asymptote going on. But I can also see here at negative 5, Ooh, this is messing it up. I should not get an answer here at -5. Hold on. Ah! It's trying to fill in the black dot. Notice how it tries to do that. That's why it's considered removable. It's because it's trying to fill it in. Okay? It's undefined here, even though it's trying to showcase one. And you can do this with the calculators from TI as well. But notice how we were able to predict that at -6 there'd be an asymptote, and at -5 there would be a hole just by using the equation. And so this is our discontinuity. Now, it is important to note, in both cases, you may always go back and do the problems using the numerical approach. Right? You can just type in numbers, get close to values. In fact, a lot of the homework problems have you doing that, so don't forget the numerical approach is an option. But you also have the option of doing it via the techniques I've shown you. Now, for some problems, that's easy to do. For others, it's not. So always have the graph available for yourself and the numbers available for yourself to see if you're going to end up with discontinuity. You can end up with discontinuity in two ways. If the limit doesn't exist, or if they don't agree with the actual value. Remember that definition of continuity. It's really important for tonight's homework. This will be it for today. And I have a nosebleed. That's perfect timing. So look forward to seeing you guys tomorrow. We'll continue our discussion of continuity. And I'll see you then.